Hello everyone. Welcome to the second task of the practical lab on cloud systems engineering. In this week's task, we will build a distributed key value store using a technique known as sharding. Through this task, you will learn to improve the performance of a key value store by sharding the keys across multiple servers. You will learn about various key sharding and sharding strategies. And finally, you'll build your first distributed key value store. Next, let's take a look at some of the background information that will help you solve this task. First, let's see the main reasons to distribute a single node key value store. There are two major reasons to convert a simple single node key value store into a complicated distributed system. The first reason is to improve fault tolerance. In a single node key value store, the single node becomes a single point of failure. If this node crashes, then no more request for keys can be served and the system becomes unavailable. The second major reason is to improve performance. For a single node key value store, only one node serves all requests for puts and gets on key value pairs. In this case, a single node is a bottleneck as the system's throughput is equal to the single node's throughput. Distributing keys over multiple servers allows a large number of put and get requests from clients to be served in a concurrent manner. Finally, there are two main solutions that can help achieve both these goals of fault tolerance and high performance. First solution is through replication, wherein the same key value pair is replicated across multiple servers. This is the focus of the next task. In this task, you will take a look at sharding, which involves partitioning the key space across multiple servers such that put and get requests on keys are served by different servers. Next, let's take a look at sharding and some sharding strategies. So sharding is a process of partitioning the key value pairs into smaller, faster, and easily managed parts. Each part is called a shard, that is, in this case, every server that serves a request. A shard is responsible for serving put and get requests to only a subset of key value pairs. Ideally, we would like to ensure that the key value pairs are distributed in a uniform manner across all shards. Two ways to distribute keys across shards include using a hash-based partitioning scheme or a range-based partitioning scheme. Additionally, sharding provides numerous benefits. Firstly, sharding enables horizontal scaling. This means that the throughput of the system increases in a linear manner with increase in the number of shards. Horizontal scaling enables good load balancing across shards, thus resulting in low latencies for completing requests. Additionally, it ensures that the storage space that is used to maintain the shard's key value pairs scales in a linear manner with the number of shards. Secondly, sharding provides partial fault tolerance. Even if a few shards become unavailable, others can still service requests. This is because a subset of the key space is still available in the active shards. However, the next question is, what kind of sharding strategies should one pick? Ideally, we would like a sharding strategy that supports flexible reconfiguration. That is, adding or removing keys should affect the least amount of shards. This ensures that a small amount of messages are exchanged between the shards. Additionally, when a shard leaves in a voluntary manner, the sharding strategy must ensure that keys and values are distributed between the new shards with as few messages as possible. First, let's take a look at range-based sharding strategies. For this strategy, the key space is divided into ranges and assigned to shards in a sequential manner. For example, as shown in the figure, keys between A to E are assigned to shard 0, keys between F to J are assigned to shard 1, and so on and so forth. The advantage of this strategy is that it is ideal for range queries. For example, a client could fetch all values with keys between A to J, and it would only need to access shards 0 and 1. The disadvantage, however, is that range-based strategies suffer from key hotspots. This means that if keys K to P are always accessed, all requests are handled only by a single shard, thereby going against the principle of horizontal scaling and its advantages that were described before. An alternative to range-based strategies is to use a hash-based sharding strategy. A hash-based strategy uses a hash function to map keys to the respective shards. The simplest hash function one can think of is assigning a key to a shard that is ID'd as the key mod the number of shards plus 1. This solves the hotspot problem that was described in the previous slide if the hash function ensures a uniform distribution of the keys across the shards. However, this technique is inefficient for range queries, as sequential keys are distributed across different shards and result in a large number of messages being exchanged. For the purpose of this exercise, we focus only on hash-based strategies. However, the problem with the simple hash function we saw in the previous slide is that on addition of even a single new shard to the system, many keys and values will have to be remapped for the hashing and the hashing function to be valid. The solution to this problem is a technique which is called as consistent hashing, which reduces the number of remappings drastically. The advantage of this approach is twofold. Firstly, the hashing scheme is independent of the number of shards and the number of keys. This allows the system to scale easily. That is, new shards can be added easily without affecting existing shards. In consistent hashing, the shards are placed on the edges of a circle based on the hashed values of their unique IDs. The keys are hashed using the same hash function and are placed on a circle as well. Some keys overlap with the shards, whereas others do not. It is important to note that the hash function assigns both the key and the shard an m-bit identifier. For every key that doesn't overlap with the shard, it is assigned to the succeeding shard clockwise in the circle. This is also known as a successor of key K in the circle. Let us take a look at this protocol through an example. Let's consider this circle that contains 4 shards with IDs 2, 13, 38, and 53 that are placed along the edges of the circle. Additionally, consider 6 keys A, B, C, D, E, F, and X, Y, Z. Keys A and B contain their hash IDs between 2 and 13. Keys X, Y, Z contain their hash IDs between 13 and 38. Keys C and E contain their hashed IDs between 38 and 53. And key D has its hashed ID between 53 and 2. This means that shard 13 is a successor for keys A and B. Hence, it will contain the values for keys A and B. We also see that shard 38 is a successor for keys X, Y, Z and contains the values for keys X, Y, Z, and so on and so forth. Additionally, each shard knows the location of its succeeding shard in the circle. For example, shard 2 knows the location of shard 13. Let's consider that a client connects to shard 2 and requests the value for key E. Since key E is not present in shard 2, it passes on the request to the successor shard 13. Shard 13 also doesn't contain the key and passes on the request to shard 38, who also doesn't contain the key E and passes on the request to shard 53. Now we see that shard 53, it contains the key and can complete the request for shard 2. The problem with this approach, however, is that for a large number of shards, there is an order of n overhead in terms of the messages exchanged, where n is the number of servers. So to overcome this problem, we use a technique known as finger tables. So every ith shard in a system contains a finger table whose jth entry contains a successor of I plus 2 to the power j minus 1 mod m, with the first entry being the immediate successor in the circle. Using the finger table, a key lookup can be completed in order of log n time, where n is the total number of shards. This table shows a finger table for shard 2, whose immediate successor is 13. S2 is the hashed identifier for shard 2 in this case. As we see, the first entry in the finger table is the successor of the shard, which is 13 for this case. And other entries, for example, S2 plus 16, it provides the location of the 16th entry from S2. That is the key whose hashed ID is S2's hash plus 16. This key is located at shard 53. Before we move on to an example lookup using a finger table, let's look at a simple hash function that allows us to distribute keys across shards. As described before, a key is assigned to its successor shard whose ID is greater than or equal to the key's hash code. The hash code of the key can be calculated using the simple hash function shown here, where Si is the ith character in the key and m is its length. To perform a key lookup using the protocol, a client would first send the request to a random shard. If the shard's ID is equal to the successor of key k, then the shard completes the request by retrieving the value corresponding to the key k. If the key isn't found in the shard, it uses the finger table to look for the closest successor of key k and forwards the request to the corresponding shard. The worst case, the protocol steps are repeated order of log n times, where n is the number of shards. Next, let's look at an example to see how this works. Consider the 4 shard setup described in the previous slides. Let's assume that the key used in the request has a hashed ID of 37, and this request is sent to shard 2. Shard 2 sees that it is not the successor for key 37. It uses the finger table to determine key 37 successor and sees that shard 38 is the closest successor to key 37. It then forwards the request to shard 38. Shard 38, on receiving the request, sees that key 37 is within its assigned key space. It retrieves the value for key 37 and completes the request. The protocol, alongside handling get and put requests, also needs to handle shards entering and leaving the system. If a newly added node is placed between 2 shards, 1 and 2, the keys lying between 1 and 2 on the circle have to be distributed to the new node as well. Additionally, the successor of node 1 and the successor of the newly added node must be updated as well. When a node leaves the system, either gracefully or because of a crash fault, it is necessary to inform its predecessor and successor to update its finger tables in a correct manner. This could be accomplished using a coordination service such as Zookeeper. And here are some more resources on distributed hash tables, the COT protocol, and their implementation in various languages. For this week's task, you will build a distributed key value store on top of the single node key value store from task 1. You will distribute the keys across numerous shards or servers by the way of sharding. The key distribution is based on a simple hash function. And your implementation should also be able to handle both dynamic and static sharding, with dynamic sharding allowing for new servers or shards to enter the system at any time. And finally, you will implement a failure detection system to detect if a shard or server has crashed. Thank you for listening. I'll see you all at the Q&A session.